let's dive into one of the most basic but most important divides in all of chemistry, the great divide between metals and nonmetals. Now, this isn't just some boring textbook topic. This is a distinction that shapes literally everything around you, from the phone in your hand to the air you're breathing right this second. So think about this for a second. What on earth could a solid, heavy cooking pan possibly have in common with the invisible air that keeps us alive? I mean, they seem like total opposites, right? One's a thing you can hold. The other is, well, it's just air. But the answer connects them at the most fundamental level of matter. And the answer is, they're both made of elements. You know, the basic building blocks of our universe. And it turns out that, of all the 118 known elements, pretty much every single one can be sorted into one of two huge, distinct families. The metals, like the iron in that pan, and the nonmetals, like the oxygen and nitrogen that make up the air. The best way to picture this is to think of the periodic table not as a chart, but as a map. And on this map, you've got two dominant kingdoms. The metals, they control a huge territory, basically the whole left side and the middle. And then, tucked away in the upper right-hand corner, you find the smaller, but super important, kingdom of the nonmetals. Okay, so if these two families have their own territories, how can you spot one in the wild? Well, the easiest way is by their physical properties, how they look and how they act. And the differences are pretty dramatic. First up, shininess. Metals are lustrous. They've got that classic metallic gleam because they're great at reflecting light. Just think of polished gold or silver. Nonmetals, though? Totally different story. They're usually dull. I mean, a lump of charcoal or a pile of sulfur powder, there's just no shine there. All right, next up, what happens when you hit them? Well, metals are both malleable, which means you can hammer them into thin sheets, and they're ductile, so you can stretch them into thin wires. Nonmetals are the exact opposite. If you take a hammer to a solid nonmetal, it's brittle. It'll just shatter into a bunch of little pieces. Now, this next one, this is absolutely crucial for, well, pretty much all of our technology. Metals are fantastic conductors of both heat and electricity. That's why the bottom of your cooking pot is metal and why our electrical wires are made of copper. Nonmetals, on the other hand, are generally poor conductors, which makes them amazing insulators. And just look at this simple circuit here. It's the perfect demonstration. If you connect the battery to the light bulb with a piece of metal, say a copper wire, the bulb lights right up. The metal completes the circuit and lets that electricity flow. But try to do the same thing with a nonmetal, like a piece of sulfur, and nothing. The bulb stays dark. It's a conductor versus an insulator, plain and simple. But all those physical things are really just what's on the surface. What truly, truly defines a metal versus a nonmetal is its chemical personality. And when you get right down to the atomic level, it all comes down to a super simple dynamic. You've got the givers and you've got the takers. Metals are the ultimate givers. You see, their atoms usually have just 1, 2, or maybe 3 electrons hanging out in their outermost shell. So for them to become stable, the easiest thing to do is to just give those few electrons away. When they do that, they're left with a positive charge, and we call that a cation. So if metals are the givers, you can probably guess what nonmetals are. They are definitely the takers. Their atoms have outer shells that are almost full, usually with somewhere between 4 and 7 electrons. So for them, the easiest path to being stable is to find and take electrons to finish filling up that shell. And when they gain those electrons, they get a negative charge, becoming an anion. So what happens when a giver meets a taker? Well, you get an ionic bond, which is the foundation for tons of different compounds. Let's just take table salt, sodium chloride. First, you have sodium, the metal. It's desperate to give away its 1 extra electron. Then along comes chlorine, the nonmetal, which needs just 1 more to be complete. The electron literally jumps from the giver to the taker. And that changes everything. Sodium becomes positive, chlorine becomes negative. And since opposites attract, they snap together, forming a super strong ionic bond. Okay, so just when you think you've got it all sorted out, metals are givers, nonmetals are takers, easy enough. Chemistry just loves to throw a few curveballs your way. Not every element plays by the rules perfectly. And honestly, these exceptions are the really interesting part. I mean, just think about the rules we just went over. We said metals are solid, right? Well, meet mercury. We said nonmetals are dull and they're insulators. Then how do you explain iodine, which actually has a metallic shine? Or graphite? It's a nonmetal, but it conducts electricity. Even the rule about metals being hard gets smashed by things like sodium, which are so soft you can cut them with a knife. These rule breakers are what make chemistry so much fun. And then you've got a whole third group that kind of lives on the border between these two kingdoms, the metalloids. These are elements like silicon and boron, and you'll find them right along this staircase line on the periodic table. They've got a mix of properties from both sides. They might look like metals but be brittle like nonmetals. And their unique ability to sometimes conduct electricity is the entire foundation of our digital world. So here's the really crucial point. All these elemental properties, they're not just random facts for a quiz. They govern everything around us. Let's see how this all plays out in the real world. Ever seen a rusty old car or a rusty nail? That's corrosion, and it's the direct result of a metal's chemical personality, that deep-seated desire to give away electrons. Iron just can't help but react with the oxygen and water in the air, and it slowly turns into iron oxide, which we call rust. It's a perfect, if a little destructive, example of a metal's chemical reactivity in action. But here's where we humans get clever. We figured out that we don't have to just accept the properties of a pure element. We can actually harness them. We can intentionally mix different elements together to create brand new materials with way better qualities. This is the whole science of alloys. And this is really where you can see human ingenuity at work. For instance, pure copper? It's pretty soft. But what if you need something harder? Well, you just mix in some zinc, and you get brass. What if you need something that resists corrosion? Mix in some tin, and you've got bronze. And that annoying rust problem with iron? By adding a little chromium and nickel, we create stainless steel, basically solving the problem at an atomic level. So when you take a step back, it's pretty amazing. It's this fundamental opposition between metals and nonmetals, between the givers and the takers, that makes our world possible. Their differences aren't a weakness at all, they're their greatest strength. And when they come together, they form the compounds, the alloys, and all the materials that we use to build, well, everything. And that really leaves you with a final thought, doesn't it? We've gone from just using the elements we could find to actively engineering brand new materials from scratch. So the real question is, what's next? What huge global challenges, from storing clean energy to exploring deep space, could we solve if we just design the next generation of materials, one atom at a time? It's a pretty exciting future to think about.